welcome back. A few episodes ago I showed this massive tower of vintage HP test equipment, and I asked y'all which one you wanted to see first. And well, there were a ton of votes in the comments, which was excellent. Thank you guys so much for that. And I kept a tally. I tallied it all up to find out what the winner was, and well, you guys have seen the thumbnail. You know what the winner is. It was this big guy here. This is the 521A frequency counter. We'll set that down because it's quite heavy. I'm really excited that you guys chose this one because there's a lot of insane analog and digital trickery going on inside of it that I really want to take a look at. But in order to get to that, we have to first pull the case off of it, and there is a massive deep clean that needs doing. Also, we need to paint the case today because the weather is nice today, but it's not going to be nice tomorrow. So we got to pull the case off of it, get it stripped and painted, and then we got to clean up the inside, and then maybe we can dig deeply into what exactly is going on inside. And hopefully by the end of the video, we'll have a really cool working frequency counter. Now, when I did the HP 150A oscilloscope, I intended for that to just be one episode, and that ultimately ended up spanning like 5 episodes. So I'm under no illusions that we'll finish this completely in today's episode. I am hopeful, but you know, let's be realistic here. Things tend to go sideways when I work on HP equipment. So we'll give it our best shot, but well, I'm burning daylight just sitting in here, so let's get out to the garage and get to work. All right, I think we're ready to start putting this thing back together and give it a test. Now, I did go through and replace most of the black beauty capacitors. There's actually 3 black beauty capacitors in here that I have not replaced yet, and that's because they have these really cool little mounts that hold them in a specific place, and they just look so cool. I couldn't bring myself to rip them out and replace them with the little Panasonic capacitors that I'm using. So I will ultimately end up replacing these eventually, but I'm going to have to get on Mauser and search for some proper axial capacitors so I can continue to use the cool little mounts. Now there's also two selenium rectifiers in the back that I haven't replaced yet, but I haven't replaced them because I wanted to do some measurements across them to find out what kind of series resistor I'll need. And if we look in the schematic, we can see that these are CR101 and CR102, which are the rectifiers for the minus 150 volt rail and the minus 105 volt rail. So after it's fired up and running, I'll take some measurements and pick the proper resistor from that point. But for now, we're going to leave them in for the first fire up. Now, the more I read and learn about this 521A frequency counter, the more I'm absolutely falling in love with it. So we'll start by taking a look at the simplified block diagram here. You can see that we have on the far upper left here, we've got our input signal coming in. It comes into the amplitude discriminator. This essentially will cut out any signal that doesn't have a fast enough rise time. And if we look at the very beginning here, we can see that the input waveform must have a rate of rise of 0.2 volts per second or faster. Anything slower than that, and the discriminator here should essentially just cut that off. And then once the signal comes out of the discriminator here, this is our signal to be counted, and it goes into the signal gate. And essentially what the signal gate is doing is it is either blocking or allowing the signal to be counted to go through to the plug-in counting units. And so that gate opening or closing signal is actually coming from the control circuitry that's down here. Now, the control circuitry is controlled via the time base. And this is really interesting because the primary time base for the 521A is actually pulled from the wall. It uses the 60 hertz that's coming out of the wall as its time base. But if you have potentially unstable line voltage, you can get inaccurate results because it's basing its entire timing off of that. So they actually sold a plugin for it, which I happen to have, which is this plug-in unit right here. And this is the more precise time base. So if we look at the front here, we can see that it says the accuracy is plus or minus 1 count. It says approximately plus or minus 0.1% when power line is used. But then it says plus or minus 0.01% when crystal controlled electronic time base is used. And that crystal controlled electronic time base is the one that I have right here. And that crystal is sticking right out of the top right here. It is a 100 kilocycle series crystal. But that time base works in conjunction with the display time circuit here that opens and closes the gate that allows the signal to go to the plug-in units. And essentially what happens is it will open that gate for a certain amount of time. The pulses coming into the plug-in units will be counted up, and then it will close that gate. And then the number of counts that it had in a given time is the frequency that we're reading. So let's start plugging everything here into the main chassis and get an idea of how things are working. And we'll start with the amplitude discriminator here. And if we go all the way to the back of the manual, there is actually a schematic diagram for the amplitude discriminator. And it looks relatively simple. But the more I tried to figure out exactly what was going on, the more it fried my brain. So I actually rebuilt the circuit in Tina. So as I understand it, and I could be way off mark here, but the first two triodes here that receive the input signal are acting as a differential amplifier, and they're acting directly on the grids of the second two triodes, which is acting kind of like a multi-vibrator. And then our output signal's actually coming out of the multi-vibrator. So that way we can have any kind of different signals coming in. We can have sine wave, square wave, triangle wave, sawtooth, whatever. As long as it has a fast enough rise time, it will trigger the multi-vibrator to put out a nice clean square wave. Now, I could be way off the mark with my explanation of that, but in Tina, whenever I simulate it, if I put the incoming signal at 1 volt peak to peak, we get a beautiful about 50 volt peak to peak square wave coming out of it. But if I drop the incoming signal from 1 volt peak to peak to 0.8 8 volts peak to peak, it just essentially shuts the whole thing down. But I think what we're seeing here is the discriminator part of the amplitude discriminator here. But that little piece goes right up here on the top. It's interesting to note that this piece actually uses two 5963s that had gold pins. So I don't know if there was some kind of specification requirements specifically for the amplitude discriminator, because none of the other 5963s use gold pins at all. All right, now next up, let's plug in the nice time base that we have that's optional here. And if we scroll up here, we can see the crystal controlled time base schematic. And it's essentially started with a crystal controlled oscillator. This is just a multivibrator that uses the crystal oscillator to give us a nice square wave coming out of it. And then we have 3 Phantastron frequency dividers. And these are all made with 5915 heptodes and a single 6 BC7, which is a triple diode in a single package. And it's this combination of the heptode or pentagrid converter and the diode that allows them to create essentially a frequency divider. And I'm going to be honest, Phantastrons, I've been trying to wrap my head around how they work for like 4 days now, and I'm still just totally lost. The manual says something about you set up the RC delay with the intention of a specific frequency division. So I imagine that when you're designing these Phantastron frequency dividers, you have to know what the input frequency is and what you want your output frequency to be when you're designing them. But regardless of how they actually work, they have 3 of them in a row to go from 100 kilohertz to 10 kilohertz to 1 kilohertz to 100 hertz. And that is our crystal controlled time base that gives us very, very precise counting. So we'll go ahead and install this on the other side of the machine over here, and it just plugs into a little socket. And to hold it in place, it's got a little screw that you have to run through and cinch down to keep everything nice and tight. And then the final pieces of the puzzle are these amazing AC4 Decade counters, and they actually have their own specific manual, which I've got here. Now these things are incredibly confusing, and I actually did an entire video on them, so if you want to hear me ramble about them for like 25 minutes, check out the other video. But I'll give a quick summary of what exactly is going on here, because it's not exactly digital and it's not exactly analog. It's a brilliant mixture of both. Yes, it is digital in the sense that there are flip-flops, which we can see in the schematic here, and that's how the Decade counter works. It counts through it as a normal binary counter. But the display is not binary. You can see that we have 0 through 9 on the display here. So there's 2 problems that we have to tackle. The first is that, well, binary counts very strangely compared to decimal. And the second is that we have essentially a 4-bit counter going on here, but 4 bits will count up to 16, and we're only counting from 0 to 9. So we have to change how it counts in order to make it so that when we get past 9, it circles back around to 0 appropriately. And so they use a pretty weird setup with how it counts in binary. You can see that the first binary counter receives an input signal, and this is the signal that's coming in from whatever signal it is that we're counting. And then the first binary creates a very nice on-off binary pulse, exactly like we would expect. However, the second binary pulse, third binary pulse, and fourth binary pulse are a little different. You can see that instead of it being just a normal divide by 2, there's a point at which it would normally transition back to 0, but it doesn't. It stays on for another pulse. And this is how they are essentially changing it so that it counts only to 9 instead of all the way to 16 with a binary count. Now, I mentioned that they were a beautiful combination of digital and analog, and everything I've pointed out so far is really just convincing a digital binary counter to count how you want it. This is actually fairly common when you want to do binary coded decimal, but where the analog comes in is how they're using the results of the binary counter to illuminate the neons, because this is very much so not binary. We're actually making use of the fact that neons can be operated in either direction, and we're using differing voltages on either side to either illuminate or extinguish the neon. So we can see here that in the schematic, it's showing the neon number 0 as being illuminated. And if we look at one side of that, it is connected up to plus 137 volts. And if we look at the other side of that, it's connected up to plus 75 volts. And well, between plus 75 and plus 137, there's enough of a voltage differential for the neon to strike. But if we look at neon number 1, it's actually sharing that plus 75 volts with neon number 0. But it's using the other plate from the first binary count as the input to it, and that is at 110 volts. And plus 75 to 110 is not enough of a voltage difference to make it strike. Now, if we look at digits number 9 and 8, we can see that they have plus 110 on one side and plus 137 on the other side, but the point in which they are shared is sitting at plus 135. And so even though it's got the same plus 137 coming into it, it's not illuminating because the voltage difference potential between 135 and 137 is not enough to strike a neon. And this happens for all of the neons. So the analog point is that we are using a variety of different voltages on different sides of each neon to either illuminate or extinguish it based upon the actual binary value that's coming out of our decade counter. Now, some of these HP frequency counters actually have Nixie tubes on them, and it would make sense you just hook it up like a Nixie tube. But that doesn't quite work because Nixie tubes, unlike neons, can't be run in both directions. And so what they do on those is they actually put LDRs in front of all of the neons and use those to trigger the Nixie. So the plug-in units on the Nixie version are actually identical to the neon version, all the way down to actually having the neon lamps in them. They just put extra LDRs and use that to control the Nixie, which I find absolutely hilarious. But if you want to know more about these specific decade counter units, like I said, check out my previous video. In the meantime, I'm going to go ahead and plug these back into the unit, and they just plug in right in the front here into little octal sockets. They just push right on down, and then we have 0 through 9 coming through the faceplate here, looking very beautiful. All right, I think it's time to finally put some power into this thing. I have not put any power into this since I bought it, so this is genuinely the first start. And it turns out that the 521A has a self-check mode. And the self-check mode will check both with the internal time base or the external crystal oscillator time base. And to switch between those, there's a little switch right here that says extal or line external. So we'll go ahead, flip that to line external. It says to set the input sensitivity control to check. So we'll set that to check. It says set the gate selector switch to 1/10 of a second. Put you on 1/10 of a second. And then it just says to adjust the display time as desired. So after we power it on and it's warmed up, we should see it display 0006. And then when we flip the gate selector to 1 second, it should show 0060. I don't know what's going to happen though, but this switch holds all the answers. So we'll go ahead and flip the power switch. The fan has come on. The power light does not seem to be illuminating. I did see the gate light come on here. Oh, we've got some numbers illuminating up here. I've got 1 and 5 illuminated at the same time. Well, now it's showing 2,000. It's doing something. All right, I did a little more playing with it, and I think I'm starting to get kind of a grasp of how it's not working correctly. Now, these are cascading decade counters. So if one decade counter has a problem that's causing the count to count incorrectly, it's going to cascade down the list. So that could be causing an issue. Now, this decade counter on the far end, you can see is just stuck at the number 2. And if I push the reset button on the bottom, we can see that it keeps everything at 0, except that this one on the end doesn't reset. But if I flip over to the crystal oscillator time base, we can see that it actually does start to move. But when it's not on the crystal time base, it just gets stuck at 2 and stays there. And that does make sense because we can see that this one only counts from 0 to 4. It would have to go all the way to 9 and wrap around for this one to go up 1. So when we're on the external power line, it's just not fast enough to get to this 4th one. But it shouldn't even be fast enough to get to the 2nd one here. So there's a problem in the reset circuit, and it's counting way too fast. We should be showing 60 here, 60 for 60 hertz, and we're showing about 426 hertz, 421 hertz, something like that. So it's counting way too fast. But the fact that it is even counting is a total win. That means that the majority of this thing is actually functioning. Now we just got to do the last 10%, which is tracking down small issues here and there. And honestly, that wasn't unexpected. Whenever I work on HP gear, it seems to be a multi-part series, which is what this series is going to be, because that will bring us to the end of this episode, as it's already getting quite long. So I hope you join me in the next episode, where we start troubleshooting this thing more seriously, trying to figure out why it's counting funky, and maybe we can finally get some proper counts on it. But in the meantime, I'm just so happy this thing is actually showing some signs of life. That is awesome. So I want to thank you guys so much for watching, and I hope to see you next time.